All right, welcome. Today, we are cracking the code on circuit theory. The fundamental rules that make literally everything from your phone to your refrigerator actually work. I mean, really think about it for a second. We use it all day, every day. But how does that electricity actually get from a plug in the wall to this screen in a way that makes sense? Honestly, it feels like magic, but it turns out it's all based on just a few core principles. And believe it or not, our key to unlocking these principles comes from a pretty unusual place, a Korean engineering exam. So we're going to use the questions from this thing, not as a test, but more like a treasure map to uncover the secrets of how electricity really behaves. Okay, first things first, we have to start with the absolute basics. These are the ground rules, the building blocks of every single circuit out there. We're talking about voltage, current, and resistance. So right off the bat, you need to know there are two basic ways to wire things up. In a series circuit, think of it like a single one-lane road. The exam's first question touches on this. The current, or the traffic, has only one path to follow, so it's the same everywhere. But the voltage, that's like the energy, it gets split up among all the stops along the way. Now, a parallel circuit is totally different. It's more like a river that splits into a bunch of smaller streams. Question 5 gives us this scenario. The voltage is the same in every single branch, but the current, that gets divided up. And just knowing that one difference, well, it changes absolutely everything. Next up is resistance. You can stick with that road analogy. Resistance is basically the amount of traffic or friction that the electricity encounters. And the formula we see from question 4 actually tells you why. A longer wire, more resistance. A thinner wire, it's like squeezing all the cars into a narrower lane. You get more resistance. And of course, the material itself matters a ton. And what happens when you get a lot of that friction, a lot of resistance? You get heat. And I mean a lot of it. This calculation from question 7 is wild. A 500 ohm resistor with just 1 amp of current, in 1 minute, it generates 7,200 calories of heat. But see, this isn't a problem. It's a feature. It's exactly how your toaster toasts or how an electric stove cooks your food. It's just turning electrical resistance into useful heat. Okay, so we've got the basics of flow and resistance down. But you really can't talk about electricity for long without bringing in its invisible partner, magnetism. They aren't two separate things, they're really just two sides of the same incredible coin. Now, I know all the different units and terms can get a little confusing. This table helps lay it all out. What you really need to know is that there are ways to measure the strength of a magnetic field, and then there are ways to measure its density, like how concentrated that field is in one area. They're just different tools to measure the same invisible force. And here's where it gets really cool. Different materials react to these magnetic fields in completely different ways. Question 17 gets into this. Just look at this chart. Copper, it barely even notices the magnetic field. But then you get something like ferrite, which is 1,000 times more responsive. And then you have a superalloy that's 1,000,000 times more responsive. This one property is the secret sauce that makes everything from powerful electromagnets to hyper-efficient motors possible. So how do we actually harness this amazing link between electricity and magnetism? Well, the answer, most of the time, is with coils of wire. They are the key to putting this incredible force to work for us. Now, when you put two coils near each other, their magnetic fields actually interact. It's a process called mutual inductance. The exam shows us the math, but don't get bogged down in it. The key idea is this. One coil's magnetic field can actually create a current in a totally separate coil without them even touching. I mean, that's the magic behind wireless phone chargers and the transformers that power our entire grid. And that leads us to this next amazing point, which we can pull from question 14. A coil, or what engineers call an inductor, doesn't just create a magnetic field, it actively stores energy inside that field. Think of it like an electrical version of a compressed spring. The more current you push through it, the more energy it holds. In this example, it's holding 25 joules of energy with 5 amps of current. Okay, so pretty much everything we've talked about so far can apply to direct current, or DC, the kind of power you get from a battery. But the power coming out of our walls is a different beast. It's alternating current, or AC, and it plays by its own unique set of rules. With AC, the voltage isn't just a steady stream,
It swings back and forth in a smooth wave. And question 16 from the exam points out a really important distinction. There's a peak value and there's an average value. So if the voltage hits a maximum, a peak of 200 volts, its average value over one of those swings is actually much lower, around 127 volts. It's super important to know which one you're talking about when you're dealing with AC.
And then you have this thing called power factor. Question 8 uses an electric fan as an example. And the best way to think about it is like a frothy beer. The apparent power is the whole mug, foam and all, but the real power is just the actual beer you get to drink. Power factor tells you how much of the electricity being delivered is actually doing useful work. A low number, like this fan's 0.71, means a chunk of that energy is just getting wasted, kind of sloshing back and forth without doing anything. So that classic AC waveform, that perfectly smooth up and down wave, is called a sine wave. But question 20 points out that modern electronics often use other shapes, like sharp square waves or triangle waves. But here's the truly mind-blowing part. Mathematically, every single one of those other complex waves is just built by adding a bunch of perfect sine waves together. The sine wave is the ultimate fundamental building block of all of it. So, when you decode it all, what have we really learned? It all comes down to a few really powerful ideas. Wiring something in series versus parallel completely changes the game. Electricity and magnetism are an inseparable duo. Coils let us harness that relationship to literally store energy, and the AC power that runs our entire world has its own special rules. These are the secrets that power, well, everything. And that brings us to the end. These principles, from people like Ohm, Faraday, and Maxwell, they were all figured out over 100 years ago, and they've powered our world ever since. It really makes you wonder, doesn't it? What new rule of electricity, what fundamental discovery is out there right now, just waiting to be found, that will power the next 100 years of technology?